Okay, off we go. So last time we were talking about cross products, and I'm going to end by showing you a couple of quickie applications. Not that this is a course in applications, of course, right? Y'all will see most of the applications you're going to do of cross products in other classes. That said, of course, we will apply cross products to other math. Is that really an application? We can debate the terminology, right? But we will use cross products with other math, certainly, quite a bit through the course, but very significantly later in the course. But just to persuade you, if nothing else, that cross product is not just a mathematical toy that mathematicians created for mathematical fun, right? I like to point out that it does arise very naturally in the physical world, right? So a real easy application is if you have some sort of an axle, we'll call it, right? And attached to that axle, you have some sort of an arm sticking off of it, like that, represented by a vector r. And then if you apply a force to that arm sticking off of the axle, whatever that force might happen to be. Y'all know what forces are, of course. Interestingly, this creates something called torque. Torque is like an angular version of force. Force is how hard you push in a straight direction. Right? Torque is kind of like how hard are you twisting something, right? So if you want to know how much does this force applied at this point connected to the axle by this R arm, how hard does that twist around the axle? Well, it's the cross product, right? The cross product is the thing that computes that. Very natural. Again, mathematicians didn't do this, right? Whatever created this universe we live in did that. We're just observing. Okay. All right. Let's see. Oh, this thing always moves. Okay. Another mysterious, weird application, I guess you might call it. But let me say it differently. Real world manifestation of this mathematical construction we've been talking about, called the cross product, is magnetic forces. This was really weird. Magnetic fields are weird. Again, don't blame me. We didn't do it. But the way magnetic fields work is if you have a magnetic field, let's say pointing like so, and if you have a charged, let's see here while I'm still on that color. If you have a charged particle moving with some velocity through that magnetic field, it's very strange, but when the velocity is that way and the field vectors are this way, you recognize the hand gesture I'm starting, right? The resulting force is in the direction of the thumb, and in fact, that force is computed by this cross product. Again, weird, but nevertheless, as another real-world manifestation of cross product. Is that cool? Is everybody on board? Hopefully you're persuaded that, again, this is not just an artificially created little mathematical toy, but this is a very real-world thing. Okay. Real quick, last thing. I guess this is the last thing we're going to say in this section. Again, you'll notice this is a students to read thing. It's just details. There's no tricky curves in this, particularly. But cross product as a binary operation, as we've been using it, is peculiar to 3 dimensions. Now, in the homework exercises, y'all will see a higher dimensional construction called a cross product, but it's really not a product. It's an operation on a list of vectors, but the point is it takes more than 2 of them. And there's a whole story there, and it's a nice exercise. But anyway, most of what we're going to do in this class, except for that one exercise, is going to involve 3-dimensional cross products, right? In 2 dimensions, there is this thing called the wedge product. It's defined by this formula, which of course you'll recognize as being a 2 by 2 determinant. Don't conflate the wedge product with determinant. Determinant is something you do to a matrix. Right? That is not what wedge is. Wedge is something that you do to a pair of vectors. And of course, if you give me a pair of vectors, I can make a matrix and vice versa. But nevertheless, they are different things. But this wedge product, not surprisingly, has some kind of cool properties. It's kind of like the triple product in some ways. It's kind of like the cross product in some ways. And when we get into chapters 6 and 7, there are going to be some what I'll call notational advantages. It's kind of cool. It'll streamline and kind of compactify some of the things that we're going to talk about. And also, there's some intuition to be had from those streamlined, compacted notations. So anyway, this will come up later. We're not going to be doing very much with the wedge product. So anyway, give this all a look, and yeah. Okay, so that finishes 1.4. You'll notice I had already assigned 1.4. That's part of homework 2. It was obvious we were going to finish 1.4. I wanted to encourage y'all to get started on those exercises. Remember, I do encourage that you work on homework exercises continually as we complete sections in class. Don't just wait until, the night before it's due, obviously, right? But, so 1.4, almost all of the exercises in 1.4 y'all could already get started on as of our last meeting, which I guess was Friday. So hope that gave y'all a little something to do over the extended weekend. I hope everybody had a good extended weekend, by the way. Okay. I was battling allergies the whole time. I see a couple nods out there. Oh, man. It's a recent thing for me, last couple of years. I've never had allergy issues until a couple of years ago. And now it's just been hitting me hard. Anyway, moving on to 1.5. This is another section that I'm going to go through pretty quickly. Again, it's not that I don't want to spend time camped out on these things and discuss them at great length. It's that we have so much to get through in this class. When we get to chapters 6 and 7, you're going to see what I'm talking about. Chapters 6 and 7 are quite a bit more substantial. Now, by the time we get to chapters 6 and 7, you will be better mathematicians. Right? So I don't want to scare you too much. Nevertheless, there's a lot more to talk about, and that time will be very, very needed. So thus the kind of the rush now. Okay, here's how we're going to start in 1.5. Suppose we have a plane, like so. Which plane am I talking about? How would I describe to you, to somebody else, some listener, which plane I'm talking about? One way to do it would be to give a vector perpendicular to the plane and a point in the plane. And I appeal to your geometric intuition. With a point and a what we call normal vector described, there is only one such plane. Right? There's not going to be multiple different planes that go through the same point and have the same normal vector. It's just not possible. Okay, so from this, how do I write the equation of the plane? And keep in mind what an equation is. It's easy to lose track of this sort of thing. Don't think of an equation, I encourage, don't think of an equation as some algebra that you write down that, ambiguously relates to the geometric object we're describing. It's much more explicit than that. An equation is a test. It is a point tester, right? So when I say we want to find an equation of the plane, what I mean is if I give you a point and then the question is, is it in the plane like so, or is it, not in the plane like so? Which of these scenarios is the point in the plane or is it not in the plane? How would we write down an algebraic point tester? And here's what I propose. Let's look at the difference vector. Let's look at r minus r naught. R is the point we're testing. R naught is the point we were given. And I make the observation that that point, we can decide on whether it's in the plane or not based on whether that difference vector is parallel to the plane. Now that's a geometric appeal, right? You just think about what it looks like. Oh, yeah, sure enough, right? If this point's in the plane, well, that point was given in the plane. That difference then is parallel to the plane. So there you go. And if this one's not in the plane, but this one is in the plane, then in some sense that difference has to point kind of, it's just not parallel to the plane, right? It's some points off in some upward direction. Okay. So that's our first test. Now this is not a very good test to write down because we don't have a convenient algebraic version of what does it look like when a vector is parallel to a plane? How do we write that down algebraically? We don't really have that. What we can do pretty easily is observe that if this is parallel to the plane, then it's perpendicular to that normal vector. And that is easy to write down. By the way, real quick, I'm going to momentarily sweep under the rug the distinction between perpendicular and orthogonal. All right, that's the little detailed devil involving the zero vector. For the moment, let's not worry about that. Parallel to the plane means perpendicular to the vector. Is that satisfying? Okay. All right. And of course, perpendicular, orthogonal. This is the definition of orthogonal. Okay. All right, so there's our equation. That's where it comes from. Pretty natural. Now we do have to clean up our mess. Right? We blurred the distinction between perpendicular and orthogonal. No fair, right? Especially since you'll notice we started off by describing this normal vector as being perpendicular. I didn't say orthogonal. I couldn't say orthogonal. Orthogonal talks about a pair of vectors. Here I'm talking about a vector and a plane. Right? We don't even have a definition of orthogonal for a situation like this. But my answer, I've written in terms of orthogonalities, right? So this, we have to be concerned that there may be a little bit of a mathematical fast one being pulled here, right? So, do we need to worry about that difference? Well, the difference, of course, comes down to zero vectors. So if we're going to look at this orthogonality, if I want to be concerned about is orthogonality good enough here? Well, let's think about that normal vector. Could that be zero? Rhetorical question. Well, wait a minute. The purpose of this vector is to help us describe sort of in some sense how this plane sits in space, right? By way of the direction that it points. It has to have a direction. If it's going to describe the plane the way it does, it has to have a direction. It can't be the zero vector. Right? Cool? Okay. All right. Well, let's think about the other one. What about r minus r naught? Could that be the zero vector? There's r minus r naught. Yeah. I mean, if r was r naught, then this would be the zero vector. So we've got to worry. Now, oh gosh, well, did we get the right answer? Should this test be a pass or a fail in the case where this vector is zero? Well, again, if this vector is zero, then r is r naught. Is r naught in the plane? Why, yes, it is. So not only can we get away with writing this with orthogonality, we must. Right? We need orthogonality, not perpendicularity. Perpendicularity would be the wrong requirement. Perpendicularity, if I were to say these two vectors need to be perpendicular, that would exclude r naught, which we don't want to do. What do you think? Everybody's happy? Okay. All right. So there you go. There's our equation of the plane. A little bit of algebra, by the way. I think y'all can, you multiply, you move things around. This, I think, is a little bit easier of a format to remember the equation. This is the form. This is my favorite personal favorite form of the equation of a plane. Now, I'll point out that the part of the idea was that these vectors N and R naught are all given. Right, if we're going to write the equation of the plane, I got to have an R naught and I got to have an N to even know what plane we're talking about. So if those are given, and in particular, if that's your normal vector, you can actually explicitly crank out that dot product. Oh, and now keeping in mind, let's see here, R, as previously noted, is just a placeholder for x comma y comma z. We're going to be using that a lot. Right? R vector typically will mean x comma y comma z. So again, you could just crank that out. N dot R is, boom, here it is, ax plus by plus cz. And this thing on the right, N dot R naught, well, we know both of those things. We can explicitly crank that out too. It'll be some value, whatever. It's some number. Let's just call it D. So this is a different form, morally the same equation. This is written out in coordinates. A lot of students are attracted to this second form, and I get it. And there's a case to be made in certain situations where this is actually really nice. Don't forget, our goal here, right, is to connect ideas to other ideas, right? And what I like about this form is that it is explicitly, not only is this an equation, not only is this a test, but this is explicitly showing how the defining characteristics of the plane, N and R naught, how do they show up? There's ideas visible in this form of the equation. And here they've kind of been sort of, they disappear in having sort of multiplied it all out. Okay. For your consideration. Okay, one really cool trick has to be noted. If you have an equation in this form, very often they'll come in this form. Notice you can just take the coefficients, whatever the coefficients are there. Oh, those coefficients, yeah, that's my normal vector. It's pretty sweet. You can just read a normal vector right off of that equation. Neat trick. Is that cool? Everybody with me? Yeah. Mm-hmm.
Why is R naught times N a scalar and not a vector?
Yeah, that's because that's how dot products work. So that specifically is a dot product. Yeah, there's I totally hear where you're coming from. You know, I too, when I was in, I don't know, elementary school, middle school, somewhere along in there, they started using dots instead of the little X, right? And yeah, you have to kind of transition into understanding it both ways, right? Because sometimes we will still use dot to represent a scalar multiplication. Here it's the dot product. Yeah, and yeah, go ahead.
It might be a dumb question, but
it's okay.
Then why is N times R a vector, not a scalar on the other side?
These are both scalars.
Oh, okay. Yeah,
now this N dot R on the left is a scalar that's computed by an expression that has three terms. So that's it's a nice observation. I too have fallen victim to this. Everybody will step on this landmine at one point or another, so you've got to be really careful about it. It's so easy to conflate pluses with commas, right? So just watch yourself. Just be aware that this is something that you can whoopsie, and that will decrease the odds of whoopsieing it. But yeah, it is a little confusing. So yeah, heads up. Yeah. Okay. Alrighty. So yeah, let's do one. Here's 3 points, which I'm just drawing figuratively. Where they actually are is not actually going to be relevant to the question here. But there's 3 points, and there's a plane that's defined by those 3 points, right? Only one plane that contains those 3 points. And how would I find the equation of that plane? Okay, so we know how to find the equation of a plane. We just talked about it. I'm going to have to find an N and an R naught, and then bam, there's my equation. Okay, so I need to find an N and an R naught. Let's start with R naught. Where am I going to find an R naught? Where am I going to find a point in this plane? I got 3 of them. Take your pick. Doesn't matter. They'll all work. They will all give the same answer. It does not matter. My own little personal bias? I like zeros and small numbers. I'd probably choose this one. Right? Doesn't matter. You'll get the same answer no matter which one you pick. Okay, next. We're going to need a normal vector. So I'm going to need a vector perpendicular to the plane. Here's where what I'm going to call the puzzle aspect of these questions comes up. It's not an algorithmic question. This is not a take these details and toss it into this hopper and turn the crank, right? This is a, you got to think cleverly, right? What tools do we have, and how can I combine those tools in what different ways to get from what I have, namely these 3 points, to what I need, which now is this normal vector. Yeah. I'm sorry, one more time?
Do you use a cross product?
Yeah, absolutely. I should apologize. Very often I will ask rhetorical questions. No, you're totally right, 100%. Yeah. So the big idea, there's a preliminary first step though, and that is to realize that these points that I was given are points. They're not really vectors. I could view them as vectors, but just don't lose sight of the fact that if the origin is over here, let's say, then these thought of as vectors are like this, right? So you can't use those green vectors. Those green vectors are not at all what we're interested in. What we've got to do is subtract pairwise. That will give us a couple of vectors parallel to the plane. Everybody see how that happened? If you have 2 points in the plane, when you subtract, the result is parallel to the plane. Now I have 2 vectors parallel to the plane, and what you said is exactly right. Since these are parallel to the plane, when we cross them, we get something perpendicular to both of them, and therefore perpendicular to the plane. So N is computed by that cross product. Yeah.
So does that mean the plane has bounds? Like,
no, I'm sorry. Drawing is hard, and drawing is usually imperfect. Prepare yourselves for this, right? When you try to draw 3-dimensional things, your result is always going to be wrong and based on some fairly reasonable complaint, right? So the complaint here, perfectly valid complaint. It looks like I have drawn the edge of like a parallelogram or something. And that wasn't what I was intending, but I don't know how else to draw a plane, right? If I want to draw a plane that extends infinitely, wouldn't I kind of have to color the whole screen black? Right? And it just becomes kind of silly. So we tend to draw planes by drawing what would a rectangular chunk of that plane look like? Does that make sense?
Yep.
Yeah. By the way, I'm going to give you all a sales pitch. Again, mathematical drawing is hard. It's also really important. This is a class that uses a lot of geometry, not just in terms of what you need to be able to do, but what you need to be able to communicate. There's a very heavy dose of geometric thinking, geometric reasoning that's going to come up in this class. And if you're going to communicate your reasoning, and if your reasoning is based on geometry, you're going to need to be able to draw to communicate your reasoning. It is hard. 3-dimensional drawing is hard. I took some time a few years ago and put together a couple of recordings of everything that I know about mathematical drawing. I've been doing it for a very long time. I'm not claiming to be the best in the world at it. I'm certainly not, right? But I've thought through a bunch of tricks, and I think they're really useful. And they get me by for multivariable calculus just fine and dandy. Right. So I put these all into a couple of recordings on the YouTube channel in the miscellaneous topics playlist. I hope you give them a look. It's about an hour or so of discussion. The first half, I guess, is tips and tricks, and then the second half, if I remember correctly, is explicit examples, laboriously gruesome detail, every single rationale behind every little stroke of the stylus, and how I produce certain difficult drawings. So anyway, I hope that'll be useful. Okay, so success. This is a cute one. I like this. I think this is an underappreciated fact. Very useful. It's going to come up several times in this class. If you have a plane and you look at the equation, and if there are no y's in the equation, right now here I wrote 0y, just to make it explicit that there are no y's in the equation. Most of the time, you just won't write that at all. Easily noted, by the way, right? If there's no y's in the equation, that's an eyeball glance. You just look, yep, there's no y's in that equation. Right? Super easy to tell. And for that low cost of an eyeball glance, you get to draw a very neat conclusion, which is that that plane has to be parallel to the y-axis. That's geometrically useful information. Right? So I think this is well worth having in your toolbox. Let's talk through why this works. Keep in mind, if this is the equation, as we noted a minute ago, the coefficients tell you a normal vector. So I know that the normal vector has no second coordinate. Don't forget that the y-axis standard basis vector, normally we draw it over here with its tail at the origin, but whatever, it's a vector. You can draw it wherever you want to, right? I find it a little bit easier to see over there, so whatever. That second standard basis vector is 0, 1, 0. And because of that 0, from there not being any y's in the equation, this dot product is always 0. And that means that this normal vector and the y-axis are always perpendicular. And that means we have a sort of a little connect the dots that we can do. We know normal vectors, planes are always perpendicular to their normal vectors. We just observed that the normal vector is perpendicular to E2. Knee bone's connected to the leg bone and all that. And as desired, I think geometric appeal, I think it follows pretty reasonably that the plane and E2 have to be parallel. That's what I like to call a geometric appeal. Think about it, persuade yourself that that's true. I think that's pretty clear if you just visualize, right? And this follows. Everybody buy it? All right, it's a cool little argument. By the way, somebody asked in my earlier class, hey, what about if there's no x's in the equation? What about if there's no z's in the equation? Are there analogous results? Absolutely. And a nice exercise, if you want to test yourself, do I have a death grip on this argument? Put this aside, take out a nice clean sheet of paper, state and prove the analogous result for, let's say the x-axis. Get a nice exercise. If you're in the market for such a thing, you don't have to do it, but I think it'd be a good little bit of practice. Okay. Here's another cool result. This is more of a puzzle. Here we're given a couple of planes. Specifically, we're given the equations of these two planes. And let's see, we are given a point. I'm interested in the line that goes through that point parallel to both of the planes. That's the line L that we want to find. But specifically, I don't just want to know the line L. I want specifically a parametrization of that line L. So how are we going to parameterize that line L? Does everybody see the question? Everybody cool with the setup? Okay. There's a million questions in this kind of category where you're given, here's the equations of this and that, and find a parameterization of the, or here's a parameterization of one thing and an equation for the other thing, find the symmetric equations for this third thing, or whatever. There's so many different variations. I think that a healthy starting point for questions like these is to first identify geometrically, what do I have? Then next, identify geometrically, what do I need? And then you start the puzzle and you play the little geometric games and how to figure out how to get from what you have to what you need. Okay, so what do we have geometrically here? Well, this equation allows me to infer that first normal vector. Right, again, you can read the coefficients, right, to produce the normal vector. Likewise, this gives me that normal vector. So I have, geometrically, I have these normal vectors N1 and N2. Oh, and of course, let's not forget I have this point, A. That's all have. What do I want? Oh, well, let's see here. I'm trying to parameterize a line. Okay, to parameterize a line, you need a point. Which I already have. Sweet. What else do we need to parameterize a line? I need a direction vector. Right? So I'm going to need to figure out how to produce that direction vector. So instead of thinking of this as a bunch of algebraic givens and an algebraic target, now instead I want to think of this as this is what I have and this is what I want to need, and the puzzle begins. How do I get from this stuff to that thing? Does everybody see how I've broken that down? And, again, there's only so many tools we have. I don't know, did y'all ever watch the old cartoon show called Scooby-Doo? It's always the only other person in the story that isn't one of the regular crew of, that drives around in the van. If there's only one other character, what else could it be? Right? So that applies sometimes in these kinds of questions. We don't have that many tools, right? And so hopefully no surprise that I have a couple of vectors and I want to find another vector. Well, let's see. These vectors are perpendicular to those planes. Those planes are parallel to this line. That line is parallel to this vector, knee bone connected to the leg bone, connected to the hip bone. Oh, I think these two vectors are perpendicular to that vector. Yeah? Cross product again. Right? So, again, very often. Let's see here. Yeah, here we go. The V computed with that cross product. Okay. Alrighty. I do want to give you all a warning about something. Before I scroll down to that section, let me point out something that these two examples have in common. This first example, I used the fact that this is perpendicular to that, and the fact that that was perpendicular to this, right? Sort of by transitivity or something, is what I like to call a transitivity argument. I conclude something about how that must relate to that, right? So this, of sorts, it's kind of a transitivity. Okay. On this one, not that different. These are perpendicular to these, which are parallel to that, and again, sort of transitively, I conclude that these must be perpendicular to that. Does everybody see how both of these examples we used a sort of a transitivity? Here's the bad news. There's lots and lots and lots of possible sort of versions of these transitivities because there's vectors and there's planes and there's lines. And then there's parallel and there's perpendicular. And then there's in 2 dimensions and there's in 3 dimensions. And I suppose in higher dimensions. Right? And that way I can do a lot of that. So don't worry about it. So there's too many versions of these possible transitivity arguments to write them all down. And I don't remember ever seeing like all of these ever written down in the same place. It'd just be tedious, right? Unnecessary. It's just not the best way to think about it. So the way I address these is I just want you all to be aware that they don't all work. There are some easy counterexamples. We'll talk about these momentarily. There are some seemingly tempting transitivities. So let's just go ahead and talk about these real quick. Those are parallel. Those are parallel. V is parallel to P and P is parallel to W. You're going to feel a strong compulsion to try to conclude that maybe V and W have to be parallel. But they're not, right? This is just not true at all. Nothing of the sort. They're not perpendicular. They're not parallel. They're not anything, right? So don't make the mistake of thinking just because it looks good on the page that it must be true. It is absolutely not. Geometry doesn't work like that. Here's another one. These are perpendicular. Right? These are perpendicular. P is perpendicular to Q. Q is perpendicular to R. Kind of feels like maybe P and R maybe they ought to be parallel or something. Maybe perpendicular or parallel. Seems like they ought to have some sort of relationship. Nothing of the sort, right? There is no immediate relationship that you can conclude between P and R. You generate all the counterexamples you want. Does that make sense to everybody? Okay, so be aware of these transitivities. Always think it through carefully if you're going to make a transitivity argument. My policy on this is you don't have to prove the transitivity you're claiming. Like if you claim, like I did up here, that this is perpendicular to that and that's perpendicular to this and therefore this must be parallel to that. That is true given that this is a plane and that's a vector and we're in 3 dimensions and all that. Given all the particulars, it is true. If what you're claiming is true, you're good. Pretty simple policy. Asterisk. What you're saying does have to be true, right? So you are responsible for using your geometric intuition and making sure that what you're claiming is actually valid. I think that's a reasonable requirement. Okay. Everybody happy? Hands? All good? Okay. Okay, how to parameterize a plane. Now, this is a new thing. Every parameterization we've done so far has been of a curve. We've talked about lines, we've talked about circles, we've talked about helices. Helices? I don't know what the plural of helix is. It feels like it wouldn't be helixes. Anyway, lots of curves. We've talked about parameterized graphs. We've never parameterized a surface previously. This will be our first parametric surface. Much later, chapter 7, we will go into much greater detail about how to parameterize surfaces. Doesn't make any sense to do it now. We won't be using them until chapter 7. But while we're here doing lines and planes, it does make sense to talk about parameterizing a plane. And this is a construction y'all have already played with. Y'all probably remember. You're probably having flashbacks already to that exercise from where it was section 1 point something, 1.2, 1.1, somewhere along in there. And look, if you've got a point in the plane, and if you have a couple of direction vectors parallel to the plane, V and W, hopefully no surprise, multiples of V and W when you add to the point A in the plane will give you another vector in the plane. So this point R there, generated by that formula, will always be in the plane. And furthermore, if V and W are independent, this construction will generate the entire plane. Again, I think that's geometrically satisfying. A lot like that example that y'all saw in the homework. Everybody buying it? Okay. So do notice we have what distinguishes this from a parametric curve is we have two parameters. S and T both can be whatever, right? Any values at all. You give me any S and any T, plug into that expression, and it will generate a point on the plane every time. All right. So, yeah, a lot like a parametric curve, except two parameters instead of one parameter. Okay. Everybody happy? Okay. Yep.
So I assume the only requirements for V and W is that they can't be parallel, but other than that, they can be anything.
They have to be linearly independent. So, which mostly means what you said. But we also have, they can't, neither one can be zero. And the easier catch-all for situations like this is independent. Yep. Yep, good question. Anybody else? Okay. Moving along. Let's see one in action. Again, with the puzzle, certain things are given, certain things are, desired. You'll recognize these 3 points. Same points we dealt with previously. We want to find a parameterization. In order to parameterize, what do I need? Well, I need a couple of direction vectors. I need vectors that are parallel to the plane. Same trick we used previously, pairwise subtracting gives me my direction vectors. They go here and here. And then, and then you parameterize using the formula we just wrote down. Everybody happy? Yep.
Since this one, both vectors come from A, but then like the earlier one, they don't both come from A, it doesn't matter.
Doesn't matter. So the weird thing about parameterizations is they're not unique. There's lots of different ways to parameterize anything, right? So, any point you pick, it'll just give you a different parameterization. Totally. And likewise, you could do A minus C and A minus B, right? They don't, but the two vectors that you use don't have to both have come from, I don't have to have subtracted the same point, right? So you got a lot of options. What you cannot do is use A minus B and B minus A. That won't work, right? So don't do anything that's sort of obviously silly. But other than that, if the 3 points do define a plane, then you're good. Okay. All right. Various other, detail-laden, but ultimately not particularly deep. Ultimately nice exercises to think through on your own, I think. The book spends a bunch of time discussing distance problems. So how far is this thing from that thing? So here the question is, how far is it from that point to that line? And when they say how far is a point from a line, what they mean is what is the length of that shortest distance, right? So we don't mean, pick whatever point you want on the line, right? Distance from a point to a line always means the shortest distance. So how would you figure out that shortest distance? Well, okay, there's little details. The idea is to take any point, or not, subtract to get that vector, right? Realize that you can use the projection formula to get that vector, right? And then green minus orange gives you the vector whose magnitude is the distance. So, clever little use of one of our tools to get from what we have to what we wanted, right? Again, it's just a puzzle. Various little puzzles. So I encourage you all to, read through. I think this is a healthy exercise. Read through. What I've written here are just kind of, little place markers, little, breadcrumbs, trail of breadcrumbs to get you through these arguments. This is a cool argument. Take a look. Think about it in different ways. Notice in both cases what we're doing is we're computing that area. I'm just computing it two different ways. And then you notice, having computed it two different ways, and therefore knowing that these two things are the same, notice that the distance that we wanted is something I can easily solve for. This is a real slick move. I wish I thought of that. It's very clever. By the way, this is a common trick in math. If you want to compute something different that relates to it. Two different ways, and then solve for what you want. Comes up fairly routinely. So again, tool for your little bag of tricks. Okay, et cetera, et cetera. So take a look at all this stuff. Again, it's just clever tricks. Okay, 1.6. I think y'all probably know most of this already. Correction, I think y'all have seen in some form or another most of this already. Most of 1.6, it's just linear algebra, right? Now, I am aware that Math219, I believe especially 218-2, is more on the algebraic side, right? And a lot to be said for that. I'm all for it. But there is a lot to be said for the geometric sort of point of view on linear algebra as well. So I'm going to talk about a few of those things. Most of 1.6 is going to be, read and remind yourself. And some of this, again, might be coming at it from a different angle from what you've seen previously. Okay. I really do like this one, though. I think this is really underappreciated. A lot of people think that when you multiply a matrix times a vector, that the proper way to think of matrix times vector is to look at the matrix, look at its rows, and then do dot products of the rows with the x vector. And that's how you compute the product, basically with dot products. Computationally, that's hard to beat. I'll remind you, computation is pretty low on our list of interests, right? At least, the turning of the arithmetic crank. I mean, actually doing arithmetic, not real high on our list of interests. Okay. What we're interested in this class is how do you connect ideas to other ideas, and matrix vector product is an idea, right? This is an object of algebra. Can I connect it to objects of geometry? Yeah, we can. And this is really cool. And again, I told my earlier section, I was embarrassingly far into my math studies when I first learned this. I think I was halfway through my math major by the time I learned this. It was embarrassing. Anyway, the point is, you can think of it in terms of columns, in the sense that a matrix vector product is a linear combination. It's a linear combination of those columns. Isn't that weird? Right? Don't think of the matrix vector product as something that you compute by a certain arithmetic that comes from a formula. A matrix vector product is a linear combination of the columns. That was a shocker for me when I first saw this. Right? And furthermore, the coordinates of the vector x are your coefficients in that linear combination. It's wild. So anyway, I feel it necessary to point this out. I want to make sure everybody knows this. This is something it comes up a lot. We're going to use it in this class in some important ways. And so anyway, make sure you're good with that. Let's see, are we, yeah, I guess we are out of time. That clock is, oh wait, it just clicked over. Okay. Y'all have a good one. Welcome back. See you on Friday.